All right, welcome back. We are now going to work on problem set 38. This one's a quick one, so let's get started. So we're going to define Gibbs free energy. So the textbook definition of Gibbs free energy is that it's the energy available to do work. So essentially when you run a reaction, you've got an enthalpy change, a change in total energy of your system. And some of that entropy is some of that energy is lost because of entropy. Everything that's left over that you can actually do stuff with that's the Gibbs free energy. So, and that's delta G. What does the sign of delta G tell you about spontaneity of a process? So, if delta G is delta G is negative, that's spontaneous. In other words, it has extra available free energy. So it's going to release energy in general instead of have to be given energy to happen. So that's going to be spontaneous. So positive would be non-spontaneous. What does it mean when delta G equals 0? Well, that's going to be equilibrium, which means the reaction is not going to proceed in the forward or reverse direction. It's found it's have to be equilibrium. It doesn't mean nothing is changing, it's just things are changing in both directions at the same rate. So you got equilibrium. And then describe two ways that delta G can be calculated for a reaction. So one is that if we have delta G of formation values, we can just do the delta G of a reaction equals the sum of n times delta G of formation of products minus the sum of n times delta G of formation of reactants. That's going to give you the delta G naught value, so that's going to be at standard state. Again, standard conditions are 1 atmosphere and 25 degrees Celsius. That's for thermodynamics. Gases were different, right? Gases was 1 atmosphere, 0 degrees Celsius. The other way we can calculate delta G is from the general delta G equation, and this is just saying what I was saying before. The free energy is going to be equal to the total change in enthalpy, the change in total energy of the system, minus this entropy term. So I have my total change in energy of the system, and then I have to subtract off some because of change in entropy, which leaves the energy that's left over that you can actually do stuff with. So, yep. So that is the nice thing about this one is that we can choose the temperature, whereas this one has to be at standard state. So if anything's ever asked you like, oh, at what temperature does this become spontaneous? I can't use this guy because this always refers to 25C, but I can use this one. All right, the figure to the right is a plot of Gibbs free energy as a function of a chemical reaction. Pure reactants are on the left, while pure products are on the right. So I'm going to say that this extent of reaction, that doesn't mean anything to you guys really, but this is 0% products, and this is 100% products. This would be 0 or 100% reactants, right? All reactants, all products. I've got 3 points on here, and I want to answer these questions for 3 points. So what's the sign of delta G? Well, if you look, this is a graph of G, not of delta G. If this is the graph of G, then delta G is the slope of the graph at any given point. So what's the slope of the graph at this point? That's negative because it's going down. So the sign is negative. Here, that's 0. It's flat. And here the slope is positive. So that's a positive delta G. Is the reaction spontaneous? No, this should say, is the reaction spontaneous? Spontaneous in the reverse direction or at equilibrium? Well, here, what's delta G? It's negative. So what this means is that at this point in the reaction, when I've got, like 10% products, so 90% reactants, 10% products, at this point, the delta G is negative. So at this point in the reaction, it is spontaneous. Right? In other words, at this point in the reaction is going to proceed forward towards products. At this point in the reaction, though, if I'm like right here, I've got, I don't know what that is, like 70 or 80% products. the reaction is no longer spontaneous in the forward direction because delta G is positive. And so what we say is that this is non-spontaneous, or you could say that the reaction is spontaneous in the reverse direction. Because if it's not spontaneous going towards products, then it will be spontaneous going towards reactants. And then lastly, this one, when delta G equals 0, that means I'm at equilibrium, which means the reaction is not going to proceed either way. So in Chem 105, we talk a lot about, we pretend like a reaction goes from 100% reactants to 100% products, but that's not actually what happens in most reactions. In most reactions, there's some ratio of products to reactants when the free energy hits a minimum. And when the free energy hits a minimum, delta G is 0, and so the reaction stops. And you actually have some products and some reactants in your mix. All right, so that is, and then justify your answers. Hopefully me talking did that. So, all right, number 3, sine of delta G for the following processes. Remember, spontaneous reactions occur without being driven by an external source of energy. Okay, so wood burns in air after being ignited. So really, just like when we were talking about entropy of the universe, we said a spontaneous reaction is one that happens. Okay, and the conditions matter. So wood burns in air after being ignited. Does that happen? Yes, so that means that delta G, which we said is negative for a spontaneous thing, that means delta G here is negative, because that happens. Water vapor condenses on sides of a glass of root beer. Yes, that happens. Right? A broken cell phone is repaired. Does that just happen? No, it doesn't happen. So that's non-spontaneous, so it's positive. Salt dissolves in water. Yes, that happens. So that's going to be negative. Photosynthesis. Now this is one of controversy because I think the key technically says that it's non-spontaneous, which is fine. Under certain conditions, that's not spontaneous, right? But under other conditions, does that happen? Sure. If I'm sitting in sunlight and my plant is alive, photosynthesis happens, which means it must be spontaneous. So I'm going to say spontaneous in sunlight. Okay, because if it's non-spontaneous, it's just not going to happen. So that's what I'm saying. Now the key says it's non-spontaneous. You can argue, maybe your TA can argue with me about it, but I think that if it's not spontaneous, it's not going to happen. So at some conditions, it must be spontaneous. Hot soup gets cold, because we can make the same argument that hot soup getting cold is not spontaneous, right? Because we could say, well, if it's on top of the stove, the hot soup gets hotter, right? So again, the conditions matter, but in normal conditions, does hot soup get cold? Yes, so that's going to be spontaneous. Muffins rising in the oven, maybe this is another one of controversy. Yeah, so do your muffins rise in the oven? Yeah, if the oven's on, the muffins rise, so that's spontaneous. And then you get an A in this course. I think this is just kind of a tongue-in-cheek type of joke. I guess the question is, if you were to stop right now, would you end up with an A in this course? And the answer is no, you wouldn't. So that's not just going to happen. But for some of you, it will happen. So under the conditions, it might be spontaneous. It doesn't really matter. Don't worry, that's not going to be on the test. All right. Okay, what are the signs of delta S, delta H, and delta G for the formation of dew on a cool night? Okay, so what's the question we're asking when we're talking about delta S? When we're talking about delta S, we're asking, is this becoming more ordered or less ordered? Well, dew forming on a cool night is going from vapor to liquid. That's becoming more ordered, which means my delta S must be negative. Okay, delta H. What's the question I'm asking here? I'm asking, is this endothermic or exothermic? Well, when I go to vapor to liquid, think, if I want to take a liquid and boil it into a vapor, I have to add heat. So if I'm going from a vapor to a liquid, it must be releasing heat, which would mean that my delta H must be negative. And delta G, what's the question we're asking? We are asking, does this happen? Okay, because if it's spontaneous, delta G will be negative. Does dew form on a cool night? Yes. So this is spontaneous, so it must be negative. All right, 4b, what are the signs for the sublimation of dry ice at 25 degrees Celsius? So again, S, does it become more or less ordered? Sublimation, that's from solid to gas, so that's going to become less ordered, so entropy increases. Enthalpy, do you put heat in or take heat out when you're going from solid to a vapor? If you're going from solid to vapor, you got to put heat in. So this is going to be positive. And then delta G, does dry ice sublime at 25 degrees Celsius? Yes, it does. So that happens. So that's going to be negative. Making ice cubes in the freezer. Okay, so I'm going from liquid to solid. Does it become more or less ordered? That's more ordered, so delta S will be negative. And then does heat go in or out when I make ice cubes? Well, if I want to melt an ice cube, I have to put heat in. So if I want to make an ice cube, I have to take heat out. So delta H will be negative. And do ice cubes form in the freezer? Yes, so delta G will be negative. All right, and last one here. I don't know how this double zero ended up over here. It should be right there, but it doesn't matter. Okay, on the right hand plot of delta H and T delta S for phase change, it's a function of temperature. So as temperature changes, my delta H term doesn't have any temperature in it, so that's not going to change, but my T delta S term does. So, and what does this tell you? This is saying that as temperature increases, my T delta S term is getting smaller and smaller and smaller. Well, that must mean that my entropy for whatever process this is must be negative, so that when T gets big, my thing in general gets smaller. Not that that matters, but what is the status of the process at the point where the two lines intersect? Well, if the two lines intersect, delta H equals T delta S. And remember that delta G is delta H minus T delta S. And so if these two things, if delta H and T delta S equal each other, that means that delta G would be equal to 0. So the answer to A would be that this is at equilibrium. Right, over what temperature range is the process spontaneous? Well, if I want it to be spontaneous, delta G assuming that this is 0 in energy, my delta H is positive. So if I want the whole thing, I want delta G to be negative first to be spontaneous, which would mean this is positive, I need this to be positive, like this whole thing needs to be positive, and needs to be greater than delta H. Basically, T delta S needs to be bigger than delta H, so that H minus T delta S is negative. So when is T delta S greater? Well, it's 60 degrees and above, or sorry, and below. So when the temperature is less than 60 degrees Celsius, that's going to be spontaneous. Of the 6 phase changes, melting, vaporization, condensation, freezing, sublimation, and deposition, which ones have thermodynamic profiles that fit this pattern? This is a confusingly worded question. I would not expect you to really be able to figure out what this is asking, but the idea is this process is non-spontaneous at high temperatures, and it becomes spontaneous at lower temperatures. So we're just asking what types of these processes at high temperatures don't happen, but at low temperatures do happen. I know high temperatures and low temperatures, it's just relative. So it's just relative. So what things become more spontaneous as you decrease the temperature? Well, if I decrease the temperature, I'm more likely to condense. Am I going to melt more if I decrease the temperature? No, I'm not. I'm going to freeze. And I'm going to, no, not sublimate. Deposition happens as I decrease the temperature. So those are the 3 phase changes that have thermodynamic profiles that fit this pattern. Okay, that was problem set 38 on some conceptual stuff on Gibbs free energy. Thanks.